Okay, so we're going to have a look at a video, the first in a series of videos on buffers. So video one here, which we're going to look at, is going to be hopefully quite a short one, really just on what buffers are and how they work, and then the chemistry behind how a buffer is set up and the chemistry behind how a buffer actually works. So we'll look here first and foremost at just what a buffer actually is, and the definition of a buffer. So you'll find this in the SIA definitions as well. This one probably matches it pretty well, but learn your SIA definition. Okay, so a buffer is something that resists change in pH with small additions of acid or alkali. So it doesn't completely prevent pH changing, but it does resist changes in it, and if you add a huge amount of acid or alkali, well then the buffer will be destroyed and it won't actually stop the pH changing at all. So it's not this sort of magical solution that you can continue adding acid or alkali to and the pH doesn't change. That just does not happen. Okay, so that's your definition, that's what it does. Now we need to know the chemistry behind how a buffer actually works and what they're formed from, and the chemistry behind how a buffer actually, when I add some acid to something or some alkali to something, how does that buffer actually prevent the pH from changing or allow it to change a very small amount. So there's two ways that a buffer is made, two ways in which a buffer forms. You need to know both of them. The first one, which we'll look at first here, is a weak acid mixed with the salt of a weak acid. So if you think about it, the weak acid has acidic properties and can react with bases or alkalis. And the salt of weak acid, if you can remember back to your conjugate acid base theory, the salt of a weak acid is the conjugate base of the weak acid. So in actual fact, what we're really doing here is we're taking an acid and we're taking a base. And if you start to think about it, that's really what you need. If you want to add acid to something and the pH not to change, you need to have something in there that reacts with the acid that you added. Likewise, if you want to add base to something and the pH not to change, you need to have an acid in there. And the mixture of a weak acid and the salt of a weak acid, which is the conjugate base of that weak acid, fits that perfectly. The second one, which is a bit more complex in terms of sort of working out why this actually sets up a buffer, is B that we have there, which I'll highlight in yellow, which is an excess of a weak acid with a strong alkali. And we'll cover the theory behind that a little bit later on. What I would say is be very careful with these calculations. These calculations, first of all, are very easily mixed up. Okay, and we're not going to do calculations in this video, but they're very easily mixed up with simple weak acid calculations. And lots of people do that all the time. Part B is very easily mixed up with working out the pH of an acid with a strong alkali. Okay, so please be careful, read the question carefully, and make sure that you do the calculation based upon the information that's given to you. So don't do a buffer calculation for a strong acid, strong alkali. Don't do a weak acid calculation for a buffer calculation. But anyway, the more you practice them, you'll be able to pick out the questions and what they're actually asking you and do the correct calculation. Right, so let's have a look at first of all. So we'll have a look. We'll take the method A that we have up here, and let's see how this sets up as a buffer. Right, so I said that I'm going to mix a weak acid and the salt of weak acid. That's exactly what I've done. And you can see, so if you think about this buffer, everything, all of this that I'm going to highlight here in blue actually is all in together. That is the buffer. They're not separate, they're all in together. And we should know by now that a weak acid will very, very partially ionize, and we get, in this case I've chosen ethanoic acid, so I get the ethanoate ion and the hydrogen ion. The salt of weak acid, on the other hand, is extremely soluble and will 100% ionize to give me again the ethanoate ion and the sodium ion. And there we go, that's what my buffer is, simple as that. And you would just adapt that for whichever weak acid and salt of the weak acid that you were given. Right, let's then look more importantly at how does this then remove acidity and alkalinity. How does it remove H plus ions and OH minus ions when they're added to this buffer, this stuff that I highlighted in blue there. Well, let's look at number one here. Let's look at adding some hydrogen ion, some acid to the buffer, and let's see what might happen. So we have got in the buffer above, we have two sources of ethanoate ions. Hopefully you can see them. Okay, two sources of ethanoate ions. Now, whatever your buffer is will have a negative ion. It may not be an ethanoate ion, it may be a cyanide ion or a propanoate ion, whatever, it doesn't matter. Okay, that will combine with or react with the H plus, okay, and will form a dative bond with the lone pair on that oxygen, and you will get the acid. Okay, and what you can see here is that the acid, because it hardly ionizes at all, the hydrogen ion that was added is now tied up in a covalent bond, so it's not a free hydrogen ion anymore. If it's not a free hydrogen ion, it can contribute to a lowering of the pH or an increase in the acidity. So that's how general buffers will remove hydrogen ion. And all you've really got to do is to be able to work out what is the A minus ion, what is the negative ion that is produced in your buffer up above in the blue highlights that does this, carries out this chemistry. Okay, right, let's have a look at what happens then when I add hydroxides. This is a little bit more complicated. First thing that I've done here is I've pulled out the sort of common wrong answer to try and remind you that is just simply incorrect. Okay, so everyone says, right, okay, well, we'll call this number 2. We add hydroxide ions, alkali. How is it that our buffer will remove alkali without allowing the pH then to go up? And everyone's eyes always light up when this comes up and they think, ah, yes, of course, I have seen sodium hydroxide so many times. Okay, so it must be that the sodium ion reacts with the hydroxide ion. Okay, well, no, the sodium ion doesn't react with the hydroxide ion for the simple reason. For the simple reason that would form sodium hydroxide, which you guys should know is a strong alkali. So we've formed our sodium hydroxide here, but because it's a strong alkali, it dissociates fully back into sodium ions and hydroxide ions. So in other words, the hydroxide ions are not removed from solution, and therefore I've added them and they're still floating around in solution with the ability to increase the pH and make the solution more alkali. So that is the one you must avoid. Don't write that. Right, there's two ways in which the hydroxide ions could be removed. If we go back up to our buffer, the preparation of our buffer, we'll see that here we have the acid, and the acid itself, the molecular acid, doesn't really ionize, only a very tiny amount. So in other words, I have lots and lots of this acid in the buffer, of those acid molecules. Now, what do we know about an acid? Well, we know that an acid will react with alkali to give me salt and water. Well, there you go. There in yellow was your hydroxide ion, now tied up in a covalent structure of water. So my hydroxide ion is not free to float around and increase the pH or make it more alkaline. The alternate thing that we could do there is the H plus ion from here, from the partial dissociation of the acid. It can also react with hydroxide ions in a neutralization reaction that we know, and we will get a molecule of water. And again, I'm just drawing the red square box around it there to show that the hydroxide ion is now tied up in a covalent molecule, and of course it can no longer increase the pH. Alright, so I've set you a couple of ones there that you could do. Okay, I've set you propanoic acid, sodium propanoate, and I want you to just do what I did above, write the equation to show how it behaves as a buffer, or sets up as a buffer, and then how does it remove acid and how does it remove alkali. And I've done the same for number 2. You could do the same for HCN and sodium cyanide, which is a weak acid, and the salt of weak acid again. Right, the method then, so if you just pause the video and do those, and then you can come back to them and I'll show you here how they actually set up as a buffer. So the propanoate ion, which is C2H5COH, okay, we would show that it partially ionizes to that and an H plus, and the sodium propanoate, very simple really, and I showing that 100% ionizes to that plus that, and then showing the removal of hydrogen ions. Okay, all I would do is my propanoid ion in this instance going to COOH. Okay, really it's just this equilibrium shifting backwards, and the hydroxide ion, okay, I would write a reaction of that propanoic acid with it to give me C2H5 COO negative plus my water, and that shows the hydroxide ion has been removed. And you would explain that with some wording, probably ask for an explanation in the question. Let's have a look at the next one, HCN. The HCN here is my weak acid. I will get that. And my salt of the weak acid is sodium cyanide. I will get that. Okay, if I add H plus ions to it, okay, that pushes that equilibrium back to the HCN. And if I add OH minus ions to it, okay, I should say I can also use this. In fact, that's a much more likely reaction to happen because there are very, very few cyanide ions from this source, and there are lots of cyanide ions from this source. The hydroxide ion will react with the hydrogen cyanide, again to give me water and a CN negative ion. So that's the chemistry of what happens within from that context with those two okay, right, so let's move on to the okay, so let's look at method 2. In method 2, I said earlier, was an excess weak acid with a strong alkali. So again, I would urge you, please make sure and read the question carefully. Do not get confused with this being a strong acid, weak alkali calculation, or strong acid, strong alkali calculation, which some people do. Okay, so let's have a look at this and see how this actually sets up and makes a buffer solution. So remember what a buffer really is. It's a weak acid plus the salt of that weak acid. Okay, so let's see how that works out in this concept, because really that's what we've got to get to in order to have a buffer. So set up a little calculation here just to show you through the numbers and show how you end up with what is the buffer that we spoke about in method 1. So I said we've got ethanoic acid, which is of course our weak acid, and we've got potassium hydroxide, which is of course our strong alkali. We've got the same volume of both, that's our concentration of both, and that's our moles of both. So you can see they're reacting a 1-to-1 ratio. You've got 0.025 moles of the ethanoic acid, and you've got 0.0175 moles of the sodium hydroxide. So therefore, you have an excess of the weak acid, as we said in the definition for this type of buffer. You have an excess of 0.025 minus the 0.0125 from here, because they're reacting a 1-to-1 ratio. So the number of excess moles of the weak acid is 0.0075 moles of that. Now when an acid and an alkali react, they of course make salt plus water. Water not so important here, but the salt is 0.00175 moles of it, because again this is my limiting reactant, my potassium hydroxide. For every mole of potassium hydroxide I can make maximum 1 mole of the salt. So if that's the number of moles of potassium hydroxide, it's in a 1-to-1 ratio, then that's the number of moles of the salt that I can make. Therefore, if I look at my solution at the end, what have I got? Well, I have got weak acid left over, and I have got salt of the weak acid left over, and then I have no potassium hydroxide left over, because in theory it has all reacted, okay, because it was the limiting reactant. Therefore, I have a buffer in exactly the same fashion as I had a buffer down below. My buffer this time is made up of my weak acid here, and this time this is the salt of my weak acid here. Okay, so hopefully that explains to you why when I react in excess of a weak acid with a strong alkali, why I still get a buffer in the same fashion that I got a buffer in my previous method 1. Okay, I hope that helps just to explain what a buffer is, how a buffer is set up and how a buffer actually removes hydrogen ions and hydroxide ions within a system. You will have to carry out some calculations, but we'll cover those in the upcoming buffer videos.